Hey, chemistry. It's Wednesday, April 8th, and we're on page 413, effects of pressure on solubility. So let's go ahead and think about it. When you take a solution of this stuff right here, okay, here it goes. That bubble, whoop, I just poured it on my keyboard. Anything for science. Okay, so what do we have here? We had some gas coming out of solution. And that gas is carbon dioxide. So how do you make a Coke anyway? Well, first of all, you take water, fill it up like this, and then you go ahead and start shoving sugar in there. Because I've already explained that there are spaces between the water molecules. And so that water acts like a very aggressive knife, and it's electrically sticky, and it just pulls apart that crystal of sugar. And so what it does is it nibbles away at it, kind of like, fish peck away at it. All right. And so it pulls that apart, and then it sticks it into the spaces between the water molecules. And when that happens, the water molecules close in on it, and it becomes what's called solvated. So first of all, water molecules have to peck apart the sugar that's going in there. In fact, I'll tell you what we'll do. Look on page 415 at the bottom. 415. Step 1. Solute particles become separated from the solid chunk because the water's going after it. And so the water molecules do their job of pecking it apart. That requires heat. It pulls heat right out of the water to do that. And then what happens is, then it has to separate the water molecules. And that requires an amount of heat from the water, pull apart the water molecules. And then the pieces of sugar molecules, they go right in between the water molecules, and the water molecules slam in on them like that. And that's a release of energy. So we've got to take in energy to pull apart the crystal, the sugar. We got to take in energy from the water to pull apart the water molecules. Then we put those molecules of sugar in there, and the water molecules slam together. That's called solvation, not salvation, solvation. Look on page 415, solvated. A solute particle that is surrounded by solvent molecules, as shown in the model figure 9, is said to be solvated. I like to say it's attacked like a bunch of piranha going after a dead body in a stream, in the jungle of Africa, or South America would be better, Brazil. Okay, and so pecks it apart, pulls it apart, crashes back together again. So there's a heat going in, endothermic, heat going in, endothermic, and then crashes back together, and it's exothermic. And so the question is, if you look on the bottom of 415, these three processes, which is bigger? When you add up the green arrow going up, that's step 1, the yellow arrow going up, add those two together, and is that bigger than the red arrow, which represents the exothermic part of the solvation? Which is bigger? In this case, the red arrow is bigger. So the exothermic nature of heat being released from the solution process is greater. And so that little blue arrow represents the delta, the difference between 1 plus 2 and step 3. And so what this is an exothermic relationship. Now, what if you have to add heat to keep this thing going? Then we say that it's endothermic. And so whenever you dissolve something, you can physically, the temperature goes up or the temperature goes down. In fact, I'm going to show you that right now. When I take hydrochloric acid 12 molar. That's what I buy it at the store. That's the concentration. And you go ahead and you add water. Go ahead and add some water. This is distilled water so that you know that I'm not cheating you or anything with some chlorine in there. Put it together. And you can feel it physically getting hotter because hydrogen chloride, hydrochloric acid dissolved in water, has a negative enthalpy of solution. Enthalpy just means heat. So a negative enthalpy of solution means heat is being released, and it is right now. And page 416 shows that. So let's go to 416 and find HCl. You're going to see that the enthalpy of solution is negative 74.84 kilojoules per mole of solute that is going into that water. What does that mean? That means we can calculate it if we watch the temperature rise or the temperature go down with a thermometer. And we'll be doing that with one of these crystalline compounds, one of these solids that we dissolve in water. Okay, let's go back to page 415 now. So we've talked about solvation. The enthalpy of solution is a direct relationship with solvation. And so you got positive enthalpies of solution. So when something dissolves, it either takes in heat, or negative enthalpies of solution, which means it releases heat when it dissolves. Let me see if you've got this. Go back to page 416 again and take a look at table salt, sodium chloride. Right there on the table on the right-hand side. It's positive 3.88. So it doesn't change the temperature of the water very much when salt dissolves, but positive means it takes in heat from the water in order to dissolve. And so it is going to cool off. What about potassium hydroxide, KOH? Look right above it, KOH. Is that a negative enthalpy of solution? I call it heat of solution. It is. It's negative 57.61 kilojoules per mole of KOH to dissolve at 25 degrees Celsius. So if it's negative, what does that mean? While it's dissolving, that crystal will release more energy than it takes in from the water. And so it's going to cause the water temperature to go up. So a negative means the temperature will go up. A positive means the temperature will go down. And so negative means exothermic, releasing heat, and positive means endothermic, taking in heat. Page 416 I'm on. Now let's read the definition of enthalpy of solution. The net amount of energy absorbed as heat by the solution when a specific amount of solute dissolves in the solvent. That's a pretty easy definition. Okay, now we're going to go back to page 413. 413, we're talking about effects of pressure on solubility. And pressure will drive a gas into solution. I was asking you, how do you make this Coke? And I said, first of all, you put a whole bunch of sugar in there, unless it's a diet like mine. A whole bunch of sugar in there. For Cokes, it's like 65 grams. You take some caffeine, which is, crystalline, and you dissolve that in there, and you take some preservatives and dissolve, and you can take some other material like phosphoric acid. It's kind of like to give it a flavoring, and you put that in there. But caramel flavoring, you stick that in there and you stir it all together. And last but not least, you put in gas. What you do is you take a compressor and you push the air in there under pressure, like 5 to 10 atmospheres, 10 times the atmospheric pressure. You push that carbon dioxide in there. And so that you get that tickle to your tummy, the bubbly sensation when you drink this. And when it's released all at once, it's called effervescence. Look on the bottom of 413 and let's see what effervescence is. It's the rapid escape of a gas from a liquid in which it is dissolved. So the gas comes out rapidly because they put it in there under 5 or 10 atmospheres of pressure and they quickly put the cap on. So that when you undo the cap, it's lower pressure outside, the gas comes out of solution and bubbles all over the place. Let's drink to that. Okay, so on the top of page 413, what you have is this little equation that says gas plus solvent. What does it mean when it's a two-way arrow? It means it's in equilibrium. So you put the gas and the solvent together, like carbon dioxide and the water, and it produces a solution of carbon dioxide water, carbonated water. But then once the gas gets in there, it wants to come back out of solution and gather up there at the top underneath the cap. That's why there's always a little space up there, because the gas wants to come out of solution, and that's the arrow coming back this way. And so now you have a gas under the cap and you have the water underneath it. But then the gas on the top of the water starts to come back into the solution. And that's the arrow like that. And the rate at which it goes into solution equals the rate at which it comes out of solution. And then that would be called equilibrium. And it takes a little while for it to set up like that inside the bottle after you put the cap on. So what happens if you put some more carbon dioxide gas above it and you press it into solution by giving it greater pressure? Yes. And so you have to have the same gas, the same solute gas, in order to hold down that carbon dioxide in solution. So if you want to put greater pressure above the carbon dioxide solution, you better make it carbon dioxide to hold it down. Okay, because that's what it says right underneath this equation on 413. It says gas plus solvent yields equilibrium with solution, and it says increasing the pressure of the solute gas above the solution will put a stress on the equilibrium and cause you to be able to put more gas in there. Okay, Henry's law. I think I'm going to start with Henry's law tomorrow, and then I'm going to do an enthalpy of solution lab in front of you. Okay, so on Henry's law, I've got to talk about scuba diving. That takes a little bit of development. So I'll see you tomorrow. Do the quiz.